We are the UNCC AFRL4 Senior Design Team, and this is our poster presentation. Going through the first part of our poster, we start with the mission. Here, it was to create a backpackable device that is able to transport up to 10 pounds of cargo through 100 yards over rough and rocky terrain in a direct action mission. So what this really boils down to is you have a soldier at point A who has supplies, a soldier at point B who has no supplies. Our job is to build a device that can travel through the battlefield terrain from point A to point B to deliver that cargo. So in response to this challenge, our conceptual design was as pictured here in this CAD model. It was a hybrid ground and aerial vehicle. It has the ability to drive and fly while carrying the pictured supplies. It is a detachable two-piece backpackable design, which was a very big positive to the design here. The UAV legs can unclamp from the UGV, fold up into a case, and the UGV chassis can go on the outside of a rucksack and allows a soldier to carry it out into a battlefield and actually use it. And when it's actually being used, it has the potential to lift up to 45 pounds at maximum throttle. The final product is as pictured here. This is as a result of our manufacturing and testing. The final specifications were we used 8 380 kV brushless UAV motors. We used 8 15.5 propellers. We had 2 24-volt DC UGV motors to pull it along the ground. We used tank treads for that. We had a 22.2-volt battery, clocking in at 12 amp hours of total battery life. The rest of the components and dimensions are as listed. We include a QR code include a QR code to a website that documents pictures and photos of our journey this SD2 semester. Finally, here we have the manufacturing and testing portions. Manufacturing was carried out more specifically for the UGV. Our UAV came prefabricated. We had to produce 2 carbon fiber legs, but the UGV was mainly fabricated out of carbon fiber and aluminum. Electrical wiring, we use 16 gauge wires for individual connections and 10 gauge for connections from the distribution block to the battery for our higher amperage connections. And we use a camera setup and functionality to allow when the remote operator has broken line of sight of the device, they can still use the cameras and have a remote feed to see where this thing is actually going. Through our testing phases, we have several pictures linked in that website prior. We were able to drive through terrain such as asphalt, dirt, rocks, grass, and stairs. During heavy stress, we're at 80 amps, and during the nominal lift, when we're using the remote controller, we can lift about 35 pounds. And as pictured before, there are multiple iterations of testing mechanisms we had to go through this semester to assure final safe production. And so one of the big challenges this semester was getting the motors to work, getting the flight computer to work. We ran into a lot of problems that took a lot of time. And so we were originally pitching this idea as an autonomous design, but we had to actually back up on that just because we ran out of time. So future modifications we'd like to add would be a LiDAR systems to go through with that autonomous control we presented at Senior Design 1. Thank you for your time.